Our project was the dynamics behind bowling the perfect strike. Our goal was to understand and test the dynamic properties required to bowl a strike. By controlling the weight of the ball and the angle of impact, we were able to determine ideal conditions and average velocity of the bowling ball. We used various equations such as kinematics equations, conservation of energy equations, and sum of force equations. Experimental trials were run that included using different weighted balls, different throwing speeds, and different angle of impacts.
So, our research, we found out that the ideal release velocity of the bowling ball should be 9.4 meters per second. An ideal velocity at impact should be 7.6 meters per second at an angle 4 to 6 degrees between the first and third pin. The ideal weight of the bowling ball should be roughly 14.5 to 15 pounds. And the length of a typical bowling alley is 60 feet or 8.288 meters, and that's to the first pin. Friction is also taken into account with varying coefficients as you move down the lane because the lane is oiled. The ball first rolls and slides and then moves into a pure rolling when it hits the pin. Forces acting on the ball and its equilibrium counterpart are shown to the right.
In our experiment trials, we had 4 different situations with 5 different trials for each situation. We controlled the weight and the impact angle to find the average velocity for each ball. The 4 different situations were a high weight straight impact, low weight straight impact, high weight angled impact, and low weight angled impact. 2 different weights used were 16 pounds and 12 pounds. After determining the time for each ball to reach the first pin, we found the velocity for each different trial and averaged those velocities for each situation. We found that the average pins knocked down were the greatest for the 4th trial, which was the low weight and angled impact situation. And our average velocity for that situation was about 6.12 meters per second. In our calculations, we used simply average velocity is equal to change in position over change in time to find our average velocity for our situation 4, which was 6.12 meters per second. And we used sum of forces in the x direction, which were equal to ma is equal to coefficient of kinetic friction times the normal force. And for experimental purposes, we used the average coefficient of kinetic friction as 0.15 because it ranges from about 0.1 to 0.3 depending on the bowling lane. We then calculated the acceleration using sum of forces in the x direction and found it to be negative 1.47 meters per second squared. And our average velocity was obviously 6.1 meters per second. Then we used theoretical calculations using the coefficient or the conservation of energy principle to find the average velocity, the ideal average velocity for the bowling ball. And using this, we found it to be approximately 9.1 meters per second. Our closest velocity to 9.1 was our 4th trial at 6.1, which proves the fact that situation 4 was the best situation to bowl a strike.
In these 2 videos, we show 2 different scenarios that we tested at the bowling alley. The first scenario was low weight straight impact. In the second situation, we used the ramp at a high weight angled impact. The ramp was used to keep a consistent angle of impact. Based on our conclusions, we found that the greatest average number of pins knocked down was when we used a low weight ball with an angled impact. We also found that the ideal angle of impact was 4 to 6 degrees, and a significant angular velocity would be required about an axis approximately 15 degrees offset from the foul line would be necessary. Note that our average velocity was 3 meters less than our calculated theoretical average velocity. We were trying to remain accurate and in turn sacrifice some speed. Challenges that were included was human error, because we weren't able to control the initial speed every time, and we weren't able to control the spin. When the ramp was used during the angle trials, the ball experienced pure rolling and was unable to reach a faster speed.